Hi class, welcome to the second half of lecture for today. So we're going to continue our discussion about stepping out of the solar system, and we're going to focus mostly on stars right now. We are going to use our understanding of stars to select stars to look at, and it's actually observations of the stars themselves that will ultimately lead to the detection of other planets around other stars. So we're going to talk about stars today, and then we'll use that as the diving board to leap into the discussion of planets next time. So in the background behind me here, this is a picture of our own sun. This was taken by a friend of mine who's an amateur astronomer in Goldendale, Washington, named Bob Yosley. So Bob is an expert solar astronomer. He loves looking at the sun. And so he takes these exquisite images of the sun because he doesn't like staying up late at night and looking at the stars all night long and being tired like the rest of us. But I show you this because I have two reasons. So one is we're going to talk about stars, and virtually everything we know about stars we've learned by never visiting one. And that includes our own sun. No one has ever been to the surface of a sun. Spacecraft have flown close, but the sun, just like the distant stars, we've learned virtually everything we know about it by looking at it with telescopes, by making images, by trying to study it remotely from the Earth. Okay, and one of the kind of great things about modern astronomy is that the technology that's available to ordinary people like me and you, or like my friend Bob here, is exquisite. It's the sort of technology that professional astronomers use. And so we're going to talk about some of the things that astronomers do today when they look at stars. Now, I couldn't show you in the lecture, but I have them right here. One of the things we do when we look at stars is we measure their color. Because it's connected to many of the other properties of the star, as we'll discuss. So one of the ways we measure color is we measure the brightness of a star by looking at it through something called an astronomical filter. So I have here in my hands the astronomical filters. I have kind of three of them that I use with my own telescope, with an amateur telescope in the backyard. They're not that different from the ones that professional astronomers use, but I wanted you to see them. So basically, when we look at stars, we will often look at them through one of these filters and measure the properties of the star through the filter, because the star looks different in different colors of light. Okay, so here's an example. You can kind of see there, that's a yellow filter. Okay, and if I were to look through a red filter, right? So you can see that, like, if you look at my face there, you can see it. It's different brightnesses through the red filter or, say, the blue filter, right? Okay, and that's because the light carries different information depending on what color the light you're looking at. And so by using filters, you can select it out and learn different things. Okay, so I want you to see those before we talk about this when we discuss stars here a little bit later in this segment. Okay, so let me go ahead and start a couple slides. Bear those filters in mind when we come back to them. Okay, so this is a picture of the Large Magellanic Cloud. So the Large Magellanic Cloud is an irregular satellite galaxy of the Milky Way. It's a small galaxy that the Milky Way is actually slowly consuming, but it's a major player in one of the biggest discoveries in astronomy, which was how do we actually measure the distances to the stars? And we'll talk about that here in a minute. I'll show you another different picture taken by the Hubble Space Telescope of a different area of the sky, the center of our own galaxy. But in this image, you should notice that the stars are different sizes. Okay, some of them are clearly bigger than others or brighter than others. And then you should also note that they're different colors. Some of them are kind of bluish, others of them are kind of orangish, some of them are just downright reddish. Okay, and we'll come back to that point as well. So in this part of the lecture, we'll talk about some historical figures and the way that they've contributed to our discovery of the stars. The kind of interesting thing about all this is that we've known about stars since forever. We see them with our naked eyes, but our understanding, our scientific understanding of stars is really just about a century old, which is remarkable that we've learned as much as we have in just 100 years. We'll talk about what some of the properties of the stars are, and that'll lead us into a tool that we use to describe the lives of the stars. Okay? So stars are at the heart of the search for other planets because the stars are the things that we can see in our telescopes. Especially when we started looking for planets, we couldn't see a single planet around another star in the telescope. They're too small, they're too dim, they're too far away. But you can pick out stars. Stars are what we've always looked at through telescopes. And so the stars have really been the starting point. Now, as our technology gets better, we can actually image light from individual planets. We'll show you some movies of that later in the week. And we can actually see the signature of planets in the lights of stars. And we'll talk about that on Wednesday as well. Okay, so the other point is that the stars themselves are the parent of the planet, and they're the primary source of energy on the planet. And as we've discussed earlier in our discussion of life in our own solar system, it's actually the fact that the sun formed the planets at the same time that gave the planets their properties, and it's the fact that the sun is constantly depositing energy on planet Earth that life forms have the base energy to start with when they're doing their lifey stuff. Okay, and so we're expecting the same thing is true of other stars, and so that's why we're going to start with the discussion of stars. So what are the properties of stars that we can measure? So you can see them represented in the images here. This is that Hubble Space Telescope image I told you I'd show you of the center of the galaxy. We want to know something about their brightness, which you can clearly see there is a distinct difference in brightness of the stars here in this image. Some are much, much brighter than others. And then we want to understand the difference in temperature. Now, we'll talk about this, but in this picture, I can tell you which stars are hotter than other stars, because one of the great discoveries at the beginning of all of this in the early 20th century is that the color of a star is related to the temperature of a star. Okay? The size of a star definitely matters. That influences both the star's temperature, it influences how long it lives, it influences what it does to the environment around it. And then last but not least, the distance to the stars is critically important, not to the properties of the stars themselves, but to us here on Earth trying to interpret the properties of the stars. Distance plays an enormous role. And if we hadn't figured out how to measure the distances to the stars, we wouldn't be able to describe any of these other properties of the stars that we think are important to understanding the environment that planets find themselves in. Okay? So why does distance matter? Let's start there. So how bright a star is fundamentally depends on how much energy the star is giving off at any moment. Okay, so just like in this image of the sun behind me, right? Every little bit of the sun you can imagine is giving off a certain amount of energy, the same amount of energy, and that energy spreads out into the universe. But if I add up all the energy from all the little pieces of the sun, that defines the total amount of energy and defines the total brightness of the sun. So I often liken it to the difference between a 100-watt light bulb and a 40-watt light bulb. If you go around your house and unscrew all the light bulbs and look at them, some of them are brighter than others. And so the brighter ones have the higher wattage. Okay, so wattage is a physics term. Watts is how much energy per time the light bulb is giving off. Astronomers also use a unit like wattage. How much energy per unit time is a star giving off? We typically call it luminosity or brightness if we're being colloquial. Okay, but there intrinsically is a difference between a 100-watt light bulb and a 40-watt light bulb. Now, here's the crux of the problem, is that if you take two light bulbs that are the same brightness, so in the image here on the right, I went out in the backyard with two flashlights that are roughly the same brightness, and I held them the same distance away and took a picture. Okay, and then the flashlight on the left in the image there, I walked farther away. And so now in the bottom image, what you see there is one flashlight's closer and one flashlight is farther away. And so one looks brighter than the other and one looks dimmer. But not because they're intrinsically brighter or dimmer. These are identical flashlights. But if one's farther away, it looks dimmer. And similarly, if I take that same flashlight and I walk closer to you, then it looks brighter than the other one. Okay, so distance plays a huge role in our interpretation of what the physical brightness of an object is. But what we care about, if I'm a planet living near a star, I care about what your intrinsic energy that you give off. I care if you're a 100-watt star or a 40-watt star. Okay, so how bright a star is depends on the distance. And so just to state what's here in the pictures, a 100-watt light bulb viewed from 4 inches away from your face appears way brighter than if you view it from 40 yards away. And you and I talked about this a couple weeks ago. This is basically the 1/r² law of light that we discussed when we first started this in the class. Okay? So if we're going to understand the amount of energy that the star is giving off, and we're going to understand how much energy it's delivering to planets that might be around it, we have to be able to measure what's the intrinsic brightness of the star. Is it a 100-watt star or a 40-watt star? Okay, well, the person who discovered that is a person named Henrietta Swan Leavitt, and I would argue she is fundamentally the most important astronomer in history because she's the one who figured out how to measure the distance to the stars. All distances to stars are measured now based on the fundamental method that she developed. It forms what's called the first rung of the distance ladder. We use it to calibrate all the other distance measures that we have, including the distance measures that measure the distances to other galaxies. Okay, so that method, she was looking at a very special kind of star in the Large Magellanic Cloud called the Cepheid variable. These are stars that get brighter and dimmer over time. And what she discovered is that if you time how long it takes the star to get brighter and then dimmer and then brighter again, that tells you something about its intrinsic luminosity. It tells you intrinsically how bright is the star really. And so if you then look at it in your telescope, you can tell how far away it is because you know how bright it's supposed to be. You know, is it a 100-watt light bulb that's too close, or is it a 100-watt light bulb that's too far away? Because I know it's supposed to look like a 100-watt light bulb. Okay, so that's often called the Cepheid period luminosity relationship, or as we often call it in astronomy, Leavitt's law. Okay, you don't have to know what Leavitt's law is or how to use it, but it is the method by which we were able to measure the distances to the stars. Okay, so she's the one who did this. She was a group of women at Harvard in the early 1900s were called the Harvard Computers, and she was a member of that group. She was a member of an early group of women who got degrees in astronomy and were put to work in the observatory, largely because they were very smart and they could do the calculations, but you didn't have to pay women as much as men in those days. And so they were cheap for the observatory. But they're the ones who made many of these fundamental discoveries, and Henrietta Swan Leavitt was at the heart of that. Now, when we talk about measuring light, we typically want to do it in a quantitative way. Okay, so as scientists, we want to be able to express things in numbers so that we can communicate with each other and communicate precisely and accurately and not be confused by saying, I measured red light, and you and I not agreeing on what red means. Okay, so with light, we typically measure a quantity that we call the wavelength. That's usually given the Greek letter lambda if you're writing it in terms of algebra. So if you see the Greek letter lambda, someone's describing the wavelength of light to you. Okay, and so light is a wave. You may have heard that in a previous science class in your life. We don't necessarily need to understand that it's a wave, but it is. And the wavelength is basically the distances between the peaks of the wave that define the color of light that you're looking at. Okay, so red light has a longer wavelength. That is, the distances between the peaks in red light are bigger, and it has a lower energy. And then blue light has shorter wavelengths. That is, the distances between the peaks are closer together, and blue light has a higher energy. Okay, so in the figure there at the top, this is something called the electromagnetic spectrum. Some of you may have seen this before, and you can see on one side of the spectrum, the waves are long, and on the other side of the spectrum, the waves are very short. Okay, now we only are paying attention to a very small part of the spectrum, what we call the visible spectrum. This is the part of the spectrum, the colors of light, that your eye can see. But there are many other parts of the spectrum. That's something we only discovered with the invention of technology. As it turns out, they're all useful for astronomy, and we'll come back and we'll talk about some of them a little bit later in the quarter. In particular, we'll talk about radio waves because we use them in the search for extraterrestrial light. But I just want you to focus today on the visible part of the spectrum. Okay, so the visible part of the spectrum, I've blown up right there. That's what you would normally call the rainbow. It's the colors you get when you direct light through a prism, or when light refracts through one of those hanging crystals you have hanging in your windowsill, or something like that. So the visible spectrum, if I were to define it quantitatively in terms of numbers, the way astronomers and scientists like, then red light has a wavelength, the distances between the peaks, of 700 nanometers, or written in our scientific notation method there, 700 times 10 to the minus 9 meters. So take a meter stick, you divide it up into a billion parts, and 700 of those parts is the distance between two wavelengths of red light. On the other end of the spectrum, we usually call it blue light, but if you know the order of colors in your spectrum, you know we're actually talking about purple light. This is historical language that we use, an example of the imprecision that we talk about and why we use numbers. Okay, so the limiting color of light that your eye can see on the purple, the extreme purple end of the spectrum, has a wavelength of about 400 nanometers. So you take that meter stick, you divide it up into a billion bits, 400 of them make up the wavelength of that extreme purple light that your eye can see. Okay? So this is called the electromagnetic spectrum, and this little bit of it here is called the visible spectrum. Okay? Now, why do I care about this? Because when I look at stars, and those star images that I was showing you in the beginning of the lecture, they have a distinct color. And you might imagine that if I were to look there at the electromagnetic spectrum, at the visible part of the spectrum, I could say, oh yeah, it kind of looks like that orange color about right there. Well, there's a reason for that, okay? And the reason for that has to do with the fact that if you look at a star through those individual filters that I showed you at the beginning, the star will have a different brightness through each of the colors. And if I plot the brightness of the star through each of those color filters, it makes a curve just like the curves that you see in this graph. Okay, so we usually call this a brightness spectrum. Okay, it's basically how bright does the star look through one of those little filters. Okay, now you'll see there's a whole bunch of different curves here. There's 4 different curves in this graph. So I just went to 4 different stars and I measured the color of the star through all the different filters, and I get these different curves, okay? And the overall color that a star appears to be has to do with where the top of that curve actually is. Okay, so the top curve here that says, that's labeled 6,000 kelvins, okay, that's the spectrum of our own sun. If I measure the color and brightness of the sun through each of those filters, it makes that curve and it peaks up there around the yellow and the green, okay? The surface temperature of the sun is that 6,000 Kelvin that that curve is labeled with. What we've discovered in the early 20th century, this is called the black body radiation law, is that the shape of that curve is determined by the temperature of the object emitting the light. And so if you can measure one of these curves for a star, which curve you're on tells you the surface temperature of the star. This is how we know the temperature of the stars. We've never sent a student or an undergraduate to a star with a thermometer to stick the thermometer in the star and measure the temperature of the star. No, we sat here on Earth, we drank our lemonade, we looked at the star through our individual filters and constructed this curve, and then we looked at which curve it was to determine what the temperature of the star was. Okay? So the temperature of the sun is about 6,000 Kelvin. It peaks there in that yellowish green color, which is why we all draw the sun yellow when we draw pictures of it with our colored pencils. Okay? Okay, so this is called the black body radiation curve, and the correspondence between the maximum color, the wavelength, and the temperature is usually called Wien's law. So those of you who are history or taking physics or something, you may have also heard a discussion of Wien's law. Okay, now this fact that the temperature of stars was connected to the color was discovered by another of the Harvard computers named Annie Jump Cannon. So in 1896, we had been classifying spectra of stars by basically looking at certain properties of the spectrum, and they were grouped together in groups that were labeled A, B, C, D, E, F, G, all the way up to the end of the alphabet. And there was no rhyme or reason. We were trying to understand all the stars that we were looking at. We were trying to understand the differences between them, why some stars were alike and some stars were different. No one could make any sense of it. But in 1896, Annie Jump Cannon realized that maybe temperature was important. And so she grouped all the stars by temperature, okay, and rearranged that spectral order. So it no longer was in alphabetical order, A, B, C, D, F, G. It's now in what we call spectral order, which is O, B, A, F, G, K, M. Okay, and we all make up mnemonics to remember that, and I'll tell you about that in a minute. But when she did that, she made probably one of the next most important discoveries in history of astronomy, which is that the color of a star is indicative of its temperature. So these are a set of spectra taken of individual stars at different temperatures. You can see the temperatures there on the right-hand side. You can see the spectral classes on the left-hand side, O, B, A, F, G, K, M. And what you see is there is a general trend in color from very blue or purplish on the upper left down to the lower right, which are very reddish. So cool stars are red, hot stars are blue is the general trend here. And Annie Jump Cannon was the person who figured that out, okay? She was a remarkable observer. Single-handedly, she looked at 350,000 spectra, not unlike the ones that you're looking at here, and classified them into their categories O, B, A, F, G, K, M. Okay, so she was an outstanding observer and also one of the central players among the Harvard computers. Okay, so let's go back to the constellation Orion, which we talked about in the first half of the lecture. Okay, so here we're just zoomed in on Orion. The Pleiades are way off to the right in the image here, but you can see the belt there in the center and the sword of Orion. And I'll point out the red star at the top is Betelgeuse, and the blue star at the bottom is Rigel. Okay, if we were to take the individual spectra of Betelgeuse and Rigel, they follow this pattern that Annie Jump Cannon discovered. Okay, so the spectrum of Betelgeuse is very steeply over towards the red. The surface temperature of Betelgeuse is something like 3,500 Kelvin. And the spectrum of Rigel, which looks very blue to your eye, is towards those blue stars. The surface temperature of Rigel is something like 20,000 kelvins. Okay, so this is crucial to our observations of the stars. We can look at stars through the telescope. We can measure their brightness in a couple of different colors. If we know the color, is it blue, is it red, is it greenish, then that instantly tells us the temperature. Okay, and that is critical to understanding what the energy output of the star is. Okay, now it's great we discovered this, okay, but no one knew why. No one at the time that we figured this out knew why stars were this way. Why did the temperature and the color correspond to each other? And the person who figured that out was Cecilia Payne-Gaposchkin. Now, Cecilia Payne-Gaposchkin was not an observer. She was a theorist, someone like me, who spends her time working on pencils. If she was a modern astrophysicist today, I'm sure she'd spend a lot of time programming computers. But she basically worked everything out by hand. And in 1925, in her PhD thesis, she published her thesis, and she made two very bold discoveries in that thesis. One was that the stars are made mostly of hydrogen and helium. Now, this is something that you and I learned when we're in first grade now, okay? But at that time, it was generally believed that the composition of the stars was not unlike the composition of the Earth. And as you and I have discovered, the composition of the Earth is largely silicates and carbon, okay? But Gaposchkin figured out that, nope, that's not true. The stars are largely composed of hydrogen and helium. And in fact, if you look at the sun absolutely has carbon in it. It absolutely has potassium in it. It has silicon in it. It has all the stuff in it that we see on Earth, okay? But it's 99.9% hydrogen and helium. Okay, that's mostly what the stars are made of. And Gaposchkin was the person to figure that out. She used that knowledge then to understand that the reason the color and the temperature were related was because of the ionization of the atoms. Basically, ionization is you take an atom which has a nucleus of protons and neutrons. It has an electron going away with it, and it takes a certain amount of energy to rip the electrons off. That's called ionization. And so she was the one to figure out that the quality of the spectrum, the color of the stars, and the correspondence with temperature had to do with that ionization. Otto Struve, who was a director of Yerkes, not far from here in Chicago, said about her thesis, he said, "It undoubtedly is the most brilliant PhD thesis ever written in astronomy." Okay, so that is bold praise for any discovery made in astronomy, but it tells you how important the discovery that she made was, because this is at the heart of why stars work the way they do. Okay, now, as I said, this was in stark contrast with what was generally believed at the time. And Henry Norris Russell, who we'll talk about in a moment, had largely discounted the ideas that Koshkin put forward in her thesis. He said it couldn't possibly be true. He went on later to decide that it was right and published a paper about this a few years later. This is very typical of what happened to women in astronomy then. It unfortunately is still very typical of what happens to women in sciences today. But we know today that it was Koshkin who first put this forward, and indeed she is the one who deserves the credit for this discovery. Okay, now, how do people use this information? Okay, so the biggest use of this information, probably the next most important discovery in astronomy, was made by these two gentlemen. So this is Irnjar Hertzsprung on the left and Henry Norris Russell, who we were just discussing on the right. Hertzsprung and Russell were trying to understand how stellar properties were related. And so they were using information like stellar temperature, like stellar brightness, to try and understand what the story of the stars actually was. And in those days, and still today, this is one of the things that we often do in astronomy, is you make graphs. You take everything you know about stars and you make graphs, and you look for patterns. You look for structure in the graph. And these two more or less simultaneously made the discovery of a diagram that today bears their name, a graph called the Hertzsprung-Russell diagram. And the Hertzsprung-Russell diagram is arguably one of the most important tools in astronomy. Those of us who do stellar astronomy, we make these graphs all the time, whether we have 25 stars or 25 million stars, because the structure and shape of the HR diagram tells us something about the evolutionary history of stars and where they are in the stages of their lives. So let me show you the diagram, and then we'll end our discussion for the day. So the Hertzsprung-Russell diagram fundamentally plots two quantities against each other. And this was the discovery that Hertzsprung and Russell made, is that these two quantities are related. Okay, and the reasons for that are, we could discuss, but we're not going to discuss in great detail. So the graph is basically, you plot the spectral type across the bottom. Now you'll remember the thing that we learned from Annie Cannon is that spectral type is synonymous with temperature. And so sometimes you'll see these Hertzsprung-Russell diagrams with temperature plotted across the bottom. Okay, it's exactly the same thing. Sometimes you'll see them plotted with color across the bottom. They're exactly the same thing. Okay, it's just what data do you have? Do you have spectral type? Do you have color? Do you have temperature? Or what do you prefer? Okay, so if you make that plot, what that means is that stars on the left side of this diagram are hot stars, okay, or bluer stars. You can see the underlying color there. Okay, bluer stars on the left, and then on the right are cooler stars, okay, or redder stars if you're plotting color. On the vertical axis, we plot the brightness, okay? And so we plot the brightest stars near the top by convention and the dimmest stars near the bottom by convention, okay? And so if you do that, and then you grab a handful of stars from your favorite star catalog and you throw them down on this graph, then the graph shows some remarkable structure. The stars aren't just smoothly scattered all over the place, like taking glitter and just throwing it on your coffee table. Okay, the stars gather themselves into these very distinct zones. Okay, so up near the top, there's a group of bright stars called the supergiants. In the upper right center, there's a group of stars that are called the giant stars. This is where what you and I call red giants live. In the bottom, there are very dim stars called white dwarfs. These are actually dead stars. Stars like the sun will die and become these types of stellar skeletons. Okay, and then there's this large diagonal band that goes from the upper left to the lower right, and that's called the main sequence. And the sun, marked by that green star, is on the main sequence. This is where most stars live their lives. Okay, so we're not going to talk much about stellar processes and stellar evolution, but when stars are in the prime of their life, like you and I are in the prime of our life, they have a job, and their job is to get up in the morning and burn hydrogen into helium. Okay, so if you're a hydrogen burning star, then you're on the main sequence. And so most stars that we see follow along this sequence. Okay. Now, the fact that stars gather themselves like this was a complete surprise. But as it turns out, the gathering here is all about stars at different stages in their lives. They're born, they get onto the main sequence, they stay on the main sequence. When they get near the ends of their lives, they swell up into red giants and they move off the main sequence into that red patch. And then when the red giant phase ends, they shrink and they die and they go down into the white dwarf sequence there at the end. Okay, so that was the first big discovery that we made about stellar evolution, was through this diagram. But we use it for many other things now. Okay, the reason it's so useful is because we have never encountered any population of stars which did not obey the HR diagram. Okay, and to show that to you, I have a little movie here. So this is a piece of software. There are many such pieces of software out there called a virtual planetarium. Okay, so this particular piece of software is called Starry Night. It's one that I use as an amateur astronomer to figure out what I'm going to look at through my telescope when I go in my backyard. So you can see the constellations plotted over there on the right. I can basically set it to any time of day, any time of year, and it'll show me what constellations are up so I can go figure out what to look at. But one of the tools it has is a Hertzsprung Russel diagram. Okay, so I've opened that up here on the right-hand side, and what it does is it looks at all the stars in the window on the right, and then on the left, where the Hertzsprung Russel diagram is, it plots the Hertzsprung Russel diagram for those stars. And so what you can see here is that diagonal band. There's the main sequence that goes from the upper left to the lower right, and then that group of yellowish stars above it are the giant stars. Okay, so in the movie here, what I do is I simply grab the sky and I drag it around, and you'll see different stars become visible in the sky. But if you watch that HR diagram, what you see is it changes, because I'm changing different stars, so they're in different places, different stages of their lives in the HR diagram, but it still looks like the HR diagram. And that's what we mean. The HR diagram applies to any group of stars that I have that I want to look at, and they tell us the story of the stars and their lives. Okay, so this is why it's such an extraordinarily powerful tool, is it allows us to understand the lives of the stars no matter where we look in the sky. And we'll come back to it. We'll use it a couple times here in our future discussion, but we're going to use this knowledge of stars that we've developed here to talk about how to select stars to look at in our telescope, and then what are we going to look at when we look at those stars to figure out whether or not there's a planet around them. That's what we'll talk about for our next class. Okay, so I hope you're all doing well. Take care of yourselves. Good luck, and I'll talk to you again soon.